So we are on the last section of the year, topic of the year, not section, okay? I'm breaking this into like 4 subsections of an overarching topic called rational functions. Rational functions, okay? Now, we've already talked about a lot of the stuff you're going to see in this section, but we haven't talked about it in this context. So you're going to see a lot of factoring. You're going to see a lot with expressions that are rational, meaning there's a fraction involved with variables. You'll see a lot with domains and the denominator causing a domain restriction. You're going to see end behavior. Remember end behavior, we had up, up, or down, down, or like this, or like that with the polynomials. We'll see end behavior with this as well. And then we're also going to see some new stuff. We're going to see stuff that are called asymptotes, which are like boundaries. We're going to see stuff called holes in the graph, where there's no value at that location. So it's going to introduce us into like 2 or 3 new concepts along the way. Some terminology to start with, okay? This is overarching terminology that we need to understand for this topic. By the way, for those that just joined us, I was speaking about this earlier. Recognize that the notes here are all filled out. There are no slides for this one. So you're not really having to take much down as far as notes are concerned. The extra stuff I talk about, though, you want to add on, you can. Okay, the only reason I do this is because at the end of the year, sometimes we run a little bit out of time. So instead of taking all the notes, it's easier to do it this way. Now, terminology-wise, first, a rational function. When something is a rational expression, it's written as a fraction. So this is the same thing. It's any function that can be written as the ratio of 2 functions, meaning a fraction. So you have one polynomial over another polynomial. That's what a rational function is defined as. Again, a polynomial over a polynomial. That's what this says. We should understand that we see ratio, we think of fraction. The end behavior. This is something we've already talked about in class. For example, a parabola with a positive leading coefficient looks like what? A quadratic function, or a parabola, with a positive leading coefficient. The general shape, what does it look like?
Concaves up.
Good. It's concave up like this, right? Everybody would agree with that? Now, we've talked about this without this notation, though. This term end behavior simply means what happens to the function as the x value, the independent variable, goes to positive or negative infinity. So explain. Let me explain. For here, take a look what happens. As I progress along this function, is it getting larger and larger or smaller and smaller? In value. In value. When I say value, it indicates only one of those.
It's getting larger?
It's getting larger. When you say value of the function, it's the y-coordinate always, okay? Location would be x. So it's gaining location in x also. Like it's still going to the right, but it's still going up. It's going up. So we would say that as x goes to the right, this function goes up. So as x goes to positive infinity, y goes to positive infinity. And here we'll see, follow the cursor, as x goes to the left, or as x goes to negative infinity, y also now, though, goes to positive infinity. The same on both sides. So this end behavior is the same in either direction. We've talked about this, but we haven't used the phrase end behavior as much. The third phrase I want to focus on is called discontinuity. Discontinuity. If something is continuous, what does that mean? Mathematically or in common terms, everyday life. Something is continuous.
It doesn't end, it's infinite, essentially.
Okay, it doesn't end. I like that. Give me more. Anything else besides it doesn't end? That's true. If it's continuous, it goes on forever.
It stays the same.
That would mean static. You're using the word static. That stays the same. Continuous could be dynamic. It could change, but it's still continuous.
No, sorry. Does it like repeat or kind of continue like the same pattern maybe?
It can continue the same pattern or repeat. That's another way to look at it. Yep. Yep.
It just like keeps going.
Along a... There's a word I'm looking for. I'm hoping somebody would use. It continues along a...
Path.
Yeah, a path. Is the path broken ever? For like a stream that's continuous. Would the path be broken? No. If it was broken, that's like when you have a dam, right? So imagine a stream is flowing, and there's a little dam created by some beavers. After that dam, what do you notice? Is the water flowing? Not really. It's usually backed up a lot in this little pool, right? It pulls up a little bit, and there's like a stagnant point, and then it continues to flow afterwards, like a stopping point. So a discontinuity in functions is when you follow the curve, like the function, follow the function, and then you notice that there's a gap. Either there's a hole in the function, you have to jump over it in a sense, there's a gap there, or the function is unbounded and then it comes back around, which we'll see in a little bit. And that's going to lead us to this last term called an asymptote. An asymptote. And it's a line such that the distance between the curve and the line gets closer and closer and closer. Let me give you an example. Have you learned about radioactive decay in science ever at some point? Have you heard the phrase?
Yes,
Can you? Yeah, good. Carbon dating uses that. Very good. Anyone want to explain how radioactive decay works as far as the math or like the numbers behind it? What happens?
So it has a half-life, and over time, like each half-life passes per gram. So like basically like ties off, and like you can check how old it is by measuring its half-life and how much there is.
So yeah, you're pretty much having the amount of radioactivity every whatever half-life is, 14 years, 10 years, 12 years, whatever it is for that element. So it's the same thing as if you were to walk to the wall and just get closer every time by half. Would you ever make it?
No.
No, you never make it theoretically. Realistically, obviously you make it, right? But think about it. Go halfway there. You're pretty much like what? Here? Okay, go halfway there. Here. Now halfway. Is this far? Halfway. Is this far? Like theoretically, I'd never make it because I keep taking things and having them, right? If you keep having a number, you never get to zero. You get a bigger and bigger and bigger denominator in the fraction, right? It's going to get to be a smaller and smaller and smaller value, but you never get to zero. That's called asymptotic behavior. You would say that it has a limit. You would say that the limit in that case would be zero. It can't get to zero, but it's approaching zero. I'm getting closer and closer to the wall. The wall is the limit that I'm getting toward. So we're going to use the word limit in this section. We're going to use the word asymptote. The line that you're approaching, the wall would be the asymptote. I'm getting closer and closer. The function gets closer and closer and closer, but it never gets there.
So isn't it on a graph, isn't that like slowly like declining? Never...
Yeah, so we can see it two ways on a graph actually. So we'll see it, I'll give you a little preview, but we'll go into this in a lot more depth. But you could have vertical and horizontal asymptotes. It would be like when a function does this, and it doesn't actually touch the dashed line, but it gets closer and closer and closer and closer to it. It's called asymptotic. Or you could have a horizontal asymptote, and it looks very similar. Okay, a horizontal asymptote would be something where it approaches the line, but it never actually touches it. It's going to ride along the line, and it's going to get closer and closer and closer to that dashed blue line, yet never touch the dashed blue line.
And the dashed blue line is the asymptote.
The dashed blue line and the other dashed line, the vertical one, are called asymptotes. And the red line is the curve in the definition of that, right? So the distance between the curve and that asymptote or in that line. So this is the curve and this is the line. The distance is getting smaller and smaller and smaller, but they're never ever going to get close enough to touch. All right, so we're going to have to start somewhere with this. So that's the entire chapter as a preview. So we're going to start with the first section here called E-1. We're going to look at this called E-1. Now, here's what I want you to think about, guys. I've written this to be like a textbook if you're written, so that I'm going through steps at a time, taking you through each of these. I don't want you to sit here and read this, obviously. I want to go over the important stuff, but feel free to just, on your own time, or if you're confused now, read what it says here. But I'm going to give you the general gist of everything, okay? So the first thing we're going to talk about is the general shape of rational functions. And rational functions behave asymptotically, meaning there's a lot of asymptotes that occur because there are discontinuities. And if I look at this first one here, I'll see there's a vertical asymptote here, there's a vertical asymptote here, and there's actually, in this case, a horizontal asymptote here. Okay, it's hard to see it. It's pretty much on the x-axis. It is the x-axis. So that's the first graph. The second and third are similar, but just to show you that they don't have to all look identical, okay, but they all follow some sort of asymptotic behavior. Look at the third graph, please, on the right. This asymptote is obvious. This asymptote is obvious. Where's the third asymptote? The y-axis, right here. Okay? It's not shown. When an asymptote lies on an axis, you usually don't show it with a dashed line. Okay? But if the asymptote lies elsewhere, you show it with a dashed line. We're going to, in this section, or in this chapter, determine how to figure out where those asymptotes lie. That's going to be part of our goals, okay? One of our main goals, really. let's see. There's also something called a slant asymptote right here. If you take a look, I'll draw you a quick diagram of that. Here's what that would look like. It's an asymptote that's slanted, hence slant asymptote. Some books, some texts call it an oblique asymptote. That's another word for it, oblique. Oblique just means slant. So if I had a vertical and a slant asymptote on the same graph, take a look at this one, please. A vertical and a slant asymptote on the same graph. This graph or this function may look like the following, where it gets closer and closer to these asymptotes, yet it never touches. That's one possibility. That's what the rational function can look like. Notice the shape. Look at the common curvature, the common reflection that's going on about some of these origins, about rotations, about some location. You see this a lot. That curvature this way and this one here. This one is like concave upper left, concave lower right. You see like not symmetry, but you see some sort of patterns occurring. And you're going to see this with a lot of rational functions where they have these curved, almost parabolic kind of shapes in pieces. Okay, in pieces. So let's take a look at the first thing. So the first thing we're going to focus on now is going to be our domain and how that relates to the vertical asymptote. Look at this function here. What value would x have to be to make this function undefined? Rich?
Would be 2.
Yeah, because 3 times 2 is 6, and 6 minus 6 is 0, right? So if I plug a 2 into this function, I don't get a value. It's undefined, right? And all your life you've said, it's undefined, you just write the word undefined. On a graph, that indicates that there is most likely at that location a vertical asymptote. So let's jot down real quick here. That actually probably even says down here. No, this we're just talking about domain. That is going to give you a vertical asymptote. Okay, that indicates a vertical asymptote. Now, if I were to ask you what is the domain of the function, you would say x cannot equal 2. And Rich told us a minute ago you can't have a 2 there. I can have a 0 in the numerator, that's not a problem. Okay, so don't worry about the numerator right now. If you factor, but here it can't let you factor. But 0 in the denominator is what throws these off. I'm going to press on to the second. Okay. So we jotted down just now that this is a vertical asymptote. And if we think about what a vertical asymptote means, from a minute ago you saw those images. Things rode along the asymptote, right? It rode right along the vertical asymptote. So if I were to graph this, I know already that on my graph, I'm going to have a line that goes like this. There's the vertical asymptote right there. X equals 2. So I know that this function is going to ride, as it comes this way, watch. It's going to either ride up along the asymptote, or it's going to ride down along the asymptote from the left. So from the left, the approach can be that this function will either ride up the asymptote or ride down the asymptote. From the right, it can go up the asymptote or down the asymptote here. Now, in these problems, we have to consider the fact that the values of the coordinates are indicating whether or not the function is going to increase along that line or decrease. In the next slide now, let's take a look at this example. So this is the same function we just had. It's the exact same function you wrote down. And now all I've done here is listed simply the coordinates as we get closer and closer to that point of discontinuity. Okay, to that point of discontinuity. Let's see if I have this right. So when we're looking at this, we're going to see that from the left, if we get closer and closer to 2, we get values that become more and more and more what? More and more negative. And then when we're approaching the right, as we get closer and closer to 2, these numbers get more and more and more positive. So look at the graphs, please. Physically, look at the graph and the curves. We know here that from the left, the number is getting more and more negative. It's going down. That's this. These numbers are getting larger and larger and larger. So as I get closer and closer and closer, this goes up further and further and further. So this vertical asymptote is like a boundary. It's a boundary that cannot be crossed. Okay, again, this is like a boundary that cannot be crossed. Graph this on your calculator so you could physically see it, because I'm making it look nice and pretty. I use the program to make that graph, but I want you guys to see what the graph actually looks like. Okay, so please take a minute, just take a minute or so to graph this on your calculator.
What's the equation to
The original equation is 2x over 3x minus 6. Yes, sir. 2x over 3x minus 6. And your interest, or your point of interest, is x equals 2. So look around x equals 2. Can you see? Yeah, very good.
So it's 2x over 3x minus 6.
2x over the quantity 3x minus 6.
It's just in the same graph.
As that. It's just I zoomed in on that.
But they never touch, but it's the same graph.
They never touch.
But it's
Right,
the same
it's
graph.
separate.
They're going to the same, they're both approaching 2, but one is getting much, much, much larger, while the other is getting much, much, much smaller.
Are they identical?
They're pretty much symmetrical in this case,
Do
yes.
they
Wow.
You could say that there's symmetry across this location right here, some location in between them. There's a point that exists for which there's symmetry about, yes.
so weird.
And rational functions are funky looking. So we're only focused on our vertical asymptotes right now. Do you notice though, isn't there a horizontal asymptote also? Believe it or not, here, do this guys. This is a little preview. Preview. What do you think it is? Anyone know? What do you think the horizontal, we're not going to learn this today, but I want to give you a little preview of horizontal asymptotes. Go to Y2, everybody go to Y2. It's not 1.5.
Oh wait, it's 2 over 3.
Yes, where are you getting that from?
Because 2 over 3 is negative 6 equals 0.
So, but where are you getting it from? From the actual?
Oh, 2x over 3x.
Yeah, look at the actual function here. See the 2x over 3x? The negative 6 has very little significance compared when you get larger. So go to Y2 and graph just the number 2/3. Literally, in Y2, just type in 2 divided by 3 in Y2 and hit graph. And you'll see the horizontal asymptote appear.
What?
Again, in Y2, just type in 2 divided by 3 and graph it.
Yeah.
And you'll see that horizontal asymptote coming across. You can barely see it. Can you see it on yours? Can you see
Yeah.
it on yours?
No, mine's bad.
Okay, there's the first one.
Wait, how did you find out that 2/3 was the asymptote?
We're going to get to that. You just saw it. It has to do with the coefficients. See the 2 and the 3 and the fraction in each of x? Comes from that. But there's 3 cases. That's just one case. So we're going to get to that a little bit later, but I want you guys to see so you can physically see it. What do you notice though about your calculator? What doesn't it show? It doesn't show the vertical asymptote. Again, the calculator is not going to show vertical asymptotes. So you have to be able to identify them from the domain, from the denominator, what the denominator's restrictions are. Let's look at a second example, please. See, guys, by the way, if anything I'm saying is not clear, look, like here, I put a whole conclusion writing out exactly what this is. Okay, now we're going to go to the next thing. We're going to call this a whole, but we're going to get to that now. Okay, so let's look at the second example here. First start with determining the value of g of x that causes it to be undefined. Okay, we're going to classify them as an asymptote or a whole, and we'll talk about why they are what they are. So look at the denominator. What would make that denominator 0? How could you figure it out?
6 and negative 2.
What did you do to do that? Factor. Factor your denominator. Write that down in big letters, please. Start the problem by factoring the denominator. By the way, this should say g of negative 2 right here. Fix that. I apologize. I don't know how to fix that. It should say g of negative 2. So go ahead and factor your denominator. This is what you're going to get right here. When you factor the denominator, you end up with x minus 6, x plus 2. So these are our 2 discontinuities. Our discontinuities are 6 and negative 2. Now, if we approach negative 2, what we're going to see is that these values are going toward a specific location now instead. It's going toward a specific location. If you notice, look at the numerator. Take a look at the numerator. What does the numerator factor into? What does the numerator factor into? Good?
X plus 2.
Yeah. And wasn't the denominator? Yes. You've got like 2 minutes left in the class. It's the very end. Unless it's emergency, you want to go. Right? So if we look at what we have here in blue, it's factored with x plus 2 and x plus 2. You all see that? You all see that they're both there, rather? The x plus 2 being in both spots is going to cause a problem. Okay, so if you graph this function at x equals 6, at x equals 6 from this, we're going to have a vertical asymptote. But the problem is, if I take negative 2 now and plug it in, I end up getting what's called 0 over 0. That's right here. That's what I'm talking about right here. If I plug a 6 in, sure, this becomes 0, right? You need to be looking up to understand this, right? So if I plug a 6 in right here, this becomes 0, but this doesn't become 0. This becomes 16. That's what g of 6 is. But if I plug negative 2 in here, it makes the top 0 also. There's something in math called 0 over 0. It's not actually called undefined. We call this indeterminate. Okay? It's another thing. Anything over 0 is undefined. But if you actually get something where it turns out to be 0 over 0, it's actually called indeterminate. Indeterminate. Okay? There is, and that's the key. Very good. So if something cancels out like this, where it factors in the top and bottom with the same factor, it'll cause you to get 0 over 0 when you plug in whatever number goes here to make this 0. That means on the graph at negative 2, instead of having a vertical asymptote, you have the other thing we're going to call a hole. So at 6, you're going to have a vertical asymptote. So for this graph, I already know out here, there's a vertical asymptote at 6. But at negative 2, it's not going to be a vertical asymptote. It's going to be a hole. And the way it works, and you can check, is by using the number approach. Look, as x gets closer and closer to negative 2, what is g of x getting closer and closer to?
0.
Be careful. It's getting smaller, but it's not getting closer to 0. Look from both sides, left and right. What are we getting closer to? Negative what? This is the number it's approaching the whole way. These values are getting closer to negative a quarter from the smaller value. This is getting closer from a larger value and absolute value. How do we get that value? All we got to do is this. Look up to the top, please. Cancel and cancel the factors. Now, take the value that would make those factors 0 and plug it in now in simplified form. What would make those factors 0? Would it be negative 2, right? Take a negative 2 and plug it in now and cancel it. What would you get? 2 over. You get 2 over, which is negative 1/4, which is the way that this is working in this problem. So what happens is this. The point is technically negative 2, comma, negative 0.25, but this is an open circle. It's a hole on the graph. Okay, that's what it would look like right there. Okay, I drew it on the graph. Please make sure tonight, well, I don't think you can do any homework on this tonight. I want to get through a couple more examples still. Let me see.